Next up, we want to understand the dynamics of the horseshoe map, but we need to do so on its invariant set. Let's take some time to explore that idea. We've got the horseshoe, and you remember how that's defined, right? You got the square, you stretch it, and you squeeze it, and you bend it over, and you lay it down on top. Okay, well, that square is where all the action happens. Recall that we denoted that I squared, that's the interval from 0 to 1, cross the interval from 0 to 1. Now, inside of this square lies the invariant set of the map. That is, the set of points that remain within the square for all time, iterating that map forwards, iterating that map backwards using the inverse. We're interested in the points that always stay in the square. Now, I know that this is a non-empty set. How do I know that? Well, there's an equilibrium in the lower left-hand corner. That one is clearly there for all time. In fact, there's another equilibrium there as well. It's not so clear quite where, or that it does exist, but it does. And that point is definitely also in the invariant set. Now the question is, what else is in there? Well, to figure that out, we're going to have to forget a few things. Forget the bend in particular. What we're going to do is we're going to take that square and then apply the map. Squeeze it, stretch it, fold it over. And the stuff that intersects the square, we're going to keep, at least for now. But all the stuff that falls outside the square, all the stuff in that bend, throw it away. Just get rid of it. Now, what happens if we do it again? And then again, for all iterates of the map and its inverse? Well, this is where it gets a little complicated. What we need to do is, again, take the square on which the horseshoe map is defined. Consider what happens when we apply the map once. We get a pair of vertical strips that remain inside the square. Now do it again. Now we have 4 vertical strips. Do that again. How many do we have? Well, we have 8 vertical strips that remain inside that square. And you can kind of see what happens when we do this over and over and over again. And we're going to throw away everything that is not in there. Now do the same thing with the inverse. Apply the inverse, we get a pair of horizontal strips. Apply the inverse again. We have 4 horizontal strips. Do that again. Keep going. We're going to throw away everything that is outside the unit square because we want stuff that stays in there for all time, moving forwards and backwards. Now this gets rather complicated, and we need to think about what happens when we iterate this over and over and over again, starting from this very simple unit square. Now, where we're going with this is the invariant set. We're going to call this set lambda, and it's going to consist of all the intersections of these images. We take the unit square, and then we intersect it with its image under F. Then we intersect it with its image under F composed with F, which I'll write as F with a superscript in parentheses. And then another iteration and another, and we keep going. All forward images. But we're not done. We need to iterate the inverse as well. We need to take F inverse of the square, take the intersection of everything with that. Then we need to apply the inverse again. I'm going to write that as F with a -2 in parentheses in the superscript. Keep going, keep going. In the end, a compact way to write this set lambda is as the net intersection over all integers n from -infinity to +infinity of the nth iterative f of the square. Keeping in mind that if n is equal to 0, doing f or applying that map f 0 times means you do nothing. So it's just the square. And this is it. This is the set of points that remains in the square for all time. We know that it certainly contains those equilibria because they're invariant under the dynamics. But the question is, what else is in there? What does this set look like? Well, if we start off just looking at the first iterate, so I have a pair of horizontal strips and a pair of vertical strips. And then I keep taking higher and higher iterates. Now I have 4 horizontal, 4 vertical, then 8 horizontal, 8 vertical. I keep going, and this gets really complicated. Now, all the time, what I want to do is take the intersections of these various strips. That is not so easy to visualize. I mean, on the one hand, it is kind of easy, right? It's just a whole bunch of squares, but they get smaller and smaller with each additional iteration. In the limit, as we take the intersection of all these things, is there anything left? And the answer is yes. Now, you might have to zoom way in to take a look at it, but it's still there. That's our invariant set lambda. Here is the theorem, the main theorem we're going to be working towards. This invariant set of the horseshoe map contains 2 equilibria, that part's not so bad, periodic orbits of all possible periods, a dense periodic orbit set, and a dense orbit, an orbit that visits as close as you like to all possible points in the invariant set. Now, there's much more inside of here. There's sensitive dependence on initial conditions. There are all the hallmarks of chaos. This is a provably chaotic dynamical system. Now, this is not obvious. It's going to take us some work, and it's going to take us some work in the next chapter.